Now, in previous stages of the course, we've talked about reaction mechanisms, especially in organic chemistry. And when we think about reaction mechanisms, the reason they're important is because, as we know, in order for a reaction to occur, collisions need to happen. But when you think about some of the reactions that we studied before, so even the first one in this mechanism discussion that had one molecule of H2SeO3 with 6 molecules of I- and 4 molecules of H+. When we think about that reaction occurring, it would be next to impossible for the reaction to occur with one single collision, because that would involve one molecule finding 6 molecules of iodine and 4 molecules of H+, or ions of H+, all simultaneously. Okay, so when you think about it that way, it seems to make sense that reactions don't often occur in one step, but they occur in elementary steps. And this series of elementary steps that lead to a product formation are called the reaction mechanism. I used to live in Toronto, and so when I lived in Toronto and I would go home to Ottawa, I would break up the drive in steps. So I could think about it as one full journey going from Toronto to Ottawa, or I could think about it in different steps. Okay, so this is a good kind of visual of what a mechanism is, an example of that. So from Toronto, I would go from Toronto to the lakeshore, and then I would go from the lakeshore to the DVP, and then I would go from the DVP to the 401, and then the 401 to the 416, and the 416 to home. Okay, these, the lakeshore, the DVP, the 401, the 416, these are what are called intermediates. Okay, so they're not part of the overall journey. The overall journey is going from Toronto to Ottawa. And when we add up all of these elementary steps, that's what we see is the overall journey. So we've done a lot of adding up of reactions in this course. And this is another case where we can add up the elementary steps to get the overall reaction. Here's another example. When we've got 2NO plus O2 going to 2NO2. This reaction doesn't happen in one step. So it doesn't occur by 2 molecules of NO colliding with 1 molecule of oxygen to produce 2NO2. It happens in elementary steps. And the elementary steps that occur are these ones. So first of all, the 2 NO molecules collide to produce N2O2. Then this N2O2 intermediate reacts with oxygen to produce the 2NO2. Okay. So these are elementary steps, and this is the overall reaction. In this case, the N2O2 is what is called an intermediate. And an intermediate is something that appears as part of the mechanism, but doesn't appear in the overall reaction. So it's produced in one step of the mechanism, and then it's consumed in a later step. And these intermediates are often very unstable on their own, and thus very reactive. When we look at a mechanism, we can talk about the molecularity of a particular step. And so the molecularity is just really how many molecules are involved in that particular step. So let's look back at this particular mechanism. In this reaction, the molecularity of this step is 2, because there are 2 molecules that are involved. As in this one, it is also 2, because there are 2 molecules involved. Okay, the molecularity of this overall reaction is 3. So you can see how the intermediate, or elementary steps rather, have fewer molecules involved. Now, what we want to do is make a connection between the rate law and the mechanism. because the rate law actually gives us an indication of what is occurring in the mechanism, or what intermediate steps must be occurring in the mechanism. So this is the primary reason why chemists study or want to determine the rate law of a reaction. It's ultimately because they want to know what the mechanism of a reaction is. The more a chemist knows about the mechanism of a reaction and how specifically a reaction is carried out, the more they can make changes to how they perform an experiment or how they do a reaction in order to get an optimum amount of product, or a pure product, or a particular product that they're looking for. So understanding the mechanism of reaction is really, really important. So we're going to study the rates to make a rate law, and that's ultimately going to help us to postulate a reasonable reaction mechanism. So the connection is to the rate law. Okay, the rate law gives us information about what is called the slow step, or the rate determining step of a reaction. Let's look at this example. In this example, we've got a reaction where 2NO2Cl reacts to form 2NO2 and Cl2. In studying this reaction, it was determined that the rate law is rate is equal to K times NO2Cl, and it's first order in NO2Cl. So what this means is that they could use this information to propose this mechanism. This rate law is telling us that there is a step in the mechanism that involves one molecule of NO2Cl. And that particular elementary step in the mechanism is actually controlling the rate of the reaction. So knowing that there was a step that involved one molecule of NO2Cl, the following mechanism was proposed. They decided that rather than two molecules of NO2Cl colliding, that this would be realistic. One molecule of NO2Cl decomposes to form NO2 and Cl. This Cl is now a very reactive intermediate, and it reacts with a second NO2Cl molecule to produce NO2 and Cl2. So this is the proposed mechanism. From this information, we now can look back at our rate law and decide which of these steps is our rate determining step, or our slow step. It's the one that's basically controlling the overall speed of the reaction. Because the rate law involves one molecule of NO2Cl, we know that this first step is likely the slow step in the reaction. It's the one that's controlling the rate of the reaction. It also makes sense because this chlorine is likely, as an atom, it's an intermediate, and it's going to be very reactive. Okay, so not only do we have this proposed mechanism, but we can say that the first step is likely the slow step in this mechanism, and the second step is fast. Let's look at another example. We've got a reaction of 2NO plus 2H2 going to N2 and 2H2O. After some study, the mechanism was determined to occur in the following two steps. 2NO plus H2 going to N2O and H2O, followed by N2O plus H2 going to N2 plus H2O. So from this information, it's asking us to produce the overall rate law based on the mechanism. And what we know is that the slow step in a mechanism is connected to the rate law of the reaction. And it actually gives us the molecularity and the exponents of our rate law. So our slow step involves two molecules of NO reacting with one molecule of H2. So what that means is that the rate law is rate is equal to K times the concentration of NO squared times the concentration of H2. Okay, so you can see the connection between the stoichiometry of the slow step of the mechanism and the rate law, which is not the same as the stoichiometry in the overall reaction. So it's really important to distinguish between the two. The rate law is connected to the slow step of the mechanism. So let's look at another example here. We've got a decomposition of hydrogen peroxide is facilitated by iodide ions. It gives us the overall reaction. The little phrase there, facilitated by iodide ions, that's giving us an indication that there's a catalyst in this reaction, which we'll see and investigate in the mechanism. So the experiment is completed and the rate law is found to be rate is equal to K times the concentration of H2O2 times the concentration of iodide ions raised to the 1. So this particular reaction is first order in both H2O2 and I minus. And if we look at the mechanism of this reaction that's been proposed, okay, we can see the connection here. So we know that the rate determining step of this reaction is going to involve one molecule of H2O2 and an iodine ion, okay, which we see in step 1 of the reaction. H2O2 plus I minus goes to H2O plus IO minus, and then in the second step, another molecule of H2O2 reacts with this IO minus intermediate. The molecularity of each step of the reaction is 2. So that simply means that 2 molecules need to collide, okay, in each step of the mechanism. The step that's the rate determining step in the reaction is the one that's connected to the rate law. So it involves one molecule of H2O2 and an iodine ion, which is step 1 of the reaction. The substance that's acting as a catalyst in this reaction is the I minus, and we know that it is a catalyst because a catalyst is something that's used in the reaction, okay, and we know that it affects the rate, and it's not consumed in the reaction. So the I minus is used in step 1, but then reproduced in step 2, okay, which is the opposite of an intermediate. So an intermediate is something that is produced in one step of the reaction and then used up in another step of the reaction. So in this case, the intermediate is IO3 minus. Okay. When we're looking at an energy profile, we're starting with H2O2. We're going to make I minus, okay, and then we're going to do the second step of the reaction. When you want to show an energy profile, we have very little information here. Like, we don't know if it's an exothermic or endothermic reaction. But what you do know is that the activation energy of the second step is going to be smaller than the activation energy of the first step. Okay, so that's about all you have to go by. Okay, but each individual reaction is going to have its own activation energy. The last thing that we're going to discuss is catalysts and the terminology that we use to explain the effect of catalysts on the rate of the reaction. I'm skipping ahead again. I'm going to go over the Arrhenius equation in the final video. I'm skipping ahead to page 46 in your notes. So catalysts and activation energy. Now, As we've discussed, a catalyst is something that is used to speed up a reaction, but it doesn't change during the chemical reaction. So it makes a catalyst something that's reusable. We can have either a homogeneous catalyst or a heterogeneous catalyst, and that simply means that the catalyst can either be in the same phase as the reaction or different. So if you have a solution and you put a catalyst like an acid into the solution and it's also a solution, then that's a homogeneous catalyst. If you've got something where the reaction is taking place in solution but you add some kind of a solid that's acting as a catalyst, that would be a heterogeneous catalyst. Now, in order to increase the rate of the reaction, one thing that we can do is if we've got a larger number of molecules with enough activation energy, then we're going to be able to overcome that activation barrier and produce products. Now, what's happening when we add a catalyst is we are providing an alternative mechanism for the reaction. So you can have a mechanism with a catalyst or without a catalyst. And usually what the catalyst will do is provide a pathway that has a lower activation energy. Okay, so in this particular example, the reaction without the catalyst has a high activation energy, but by adding the catalyst, there's an alternative pathway with a lower activation energy. If we connect this to the Maxwell-Boltzmann diagram, okay, you'll remember we had just at a normal temperature, we had an activation energy. And we said that any molecules beyond that point had enough energy on their own to overcome the activation barrier. By adding a catalyst and providing an alternative pathway, what we've done is we've got a lower activation energy for the reaction to take. So therefore, all of a sudden, we've got more molecules with enough activation energy, enough energy to overcome the activation barrier of the reaction. So that's the correct way of explaining that a catalyst can increase the rate of the reaction. It is incorrect to say that the catalyst lowers the activation energy of the reaction, because it doesn't actually change the activation energy of the particular reaction. It's simply providing an alternative path. So for example, if you look at this reaction, making sulfuric acid out of sulfur and oxygen could occur in this three-step process. Okay, so you can take a minute and examine that three-step process. By adding a catalyst of NO2 to this system, what happens is this second step, okay, which is likely a slow rate-determining step for this reaction, can be made quicker. And the pathway that it takes, rather than this pathway of SO2 molecules reacting with oxygen directly to form SO3, is this step. Okay, so the SO2 reacts with some NO2. This will have a lower activation energy likely, and then the NO, this reactive intermediate, reacts with oxygen to produce the SO2, the NO2. Okay, and overall, what's happening here is the SO2 is converting to SO3. Okay, it doesn't look like much of a change, but what we can say is that this catalyzed reaction has a lower activation energy, so it's going to happen quicker than this one that's given up here. Okay, so a catalyst can simply change the pathway of the reaction and make it go faster in that way.